Thank you.
Okay, thank you very much. I will talk about this joint work with Monique Müller, María Julia Redondo, and Pamela Suarez. And we are interested in finding Maurer-Cartan elements because it is well known that Maurer-Cartan elements parametrize the formation. So all the algebras appearing here are finite dimensional K algebras. And what is a deformation? If we take a finite dimensional K algebra A, associative K algebra A, we consider A tensor KT, this polynomial ring, we can just put the truncated polynomial ring or even the formal series ring. And we give a structure of algebra given by this product F. And this product F is defining via this morphism Fi. And if F0 is the original product, that is, if we put t equals 0, we recover the original A, and F is associative, we say that AF is a deformation. So F being associative is equivalent to us some condition of F is that we will see that F is satisfying the Maurer-Cartan equation. So what is the Maurer-Cartan equation? We need to define first some what is an L-infinity algebra? An L-infinity algebra is a graded vector space and with some linear maps Ln of degree 2 minus n, satisfying a lot of conditions. And if we ask, for example, that Ln is 0 for n greater than 2, and we only have L1 and L2, then we recover the definition of differential graded Lie algebra. That is, L1 is a differential and L2 is a Lie bracket, graded Lie bracket, as in the last talk mentioned Can1. Okay, and a Maurer-Cartan element is an element of degree 1 satisfying this Maurer-Cartan equation. If we are dealing with DC Lie algebra, then the equation is just the differential of F plus half of the bracket of F against F. And our job is about putting some condition on the gentle algebra A such that we have only finitely many non-zero Ln. Okay, so what is a gentle algebra? It's a quadratic algebra given by a finite quiver and ideal generated by only monomial quadratic relations. And we ask that if we have an arrow alpha, we have at most one arrow beta such that alpha beta is in the ideal, and at most one arrow gamma such that alpha gamma is not in the ideal, and for each arrow beta we have at most one arrow alpha such that alpha beta is in the ideal, and at most one arrow delta such that delta beta is not in the ideal. So in particular, for each vertex, we have at most 2 incoming arrows and at most 2 outcoming arrows. Okay, and we will consider the Bardzell complex given by these spaces of where APN are the supports of n concatenations. Here, if we are dealing with gentle algebras, in particular, we are dealing with quadratic algebra, so the n concatenations are just tuples of alpha 1, alpha 2, alpha n, such that alpha I plus 1 is in the ideal. Okay, and we can prove that this complex is an L-infinity algebra, and we described this structure explicitly with María Julia Redondo in a previous work. And this structure is given, comes from the structure of the Hochschild complex, which it is well known that is a differential graded Lie algebra with the Herstein-Haber bracket. So we want to find Maurer-Cartan elements So we are dealing with elements of degree 1 in this sheaf complex. So it's degree 2 in the Bardzell complex. So we have to calculate this Ln of this some elements of degree 1. So this ln(f1)(fn) has degree 3. So we have to calculate in 3 concatenations, which are just alpha1, alpha2, alpha3, with alpha1, alpha2 a relation, and alpha2, alpha3 another relation. Okay, so as I mentioned before, we want to put some conditions on the quiver in order to have only finitely many non-zero ln of fj1, fjn. Okay, so first we saw that L2 is always 0. So if we have a bracket of any two elements of degree 1, we have 0. But L3 is not always 0, but we saw that if we asked that Q has no oriented cycles and no parallel arrows, then L3 is always 0. Here we found a lot of examples with oriented cycles or parallel arrows that have infinitely many non-zero ln, and we decided that these hypotheses are good to ask in every algebra and will appear in every proposition or result. Okay, we see that even if we have no oriented cycles nor parallel arrows, we found this example. So if we have this gentle algebra, we saw that we have infinitely many ln different from 0. And this is our only non-nilpotent examples under our hypothesis. So luckily, we could prove that if we have a gentle algebra with no oriented cycles and no parallel arrows, then if Q doesn't contain a subquiver of this form star, then ln is 0 for all n greater or equal to 5. So L2 is 0, L3 is 0, and ln is 0 for n greater or equal to 5. And what about L4? We prove that L4, if Q is a gentle algebra without oriented cycles or parallel arrows, then L4 is different from 0 if and only if we have a subquiver of the form. Okay, here always, I didn't mention, but always we are dealing with alpha1, alpha2, alpha3, 3 concatenation. And our main result is that if we have a gentle algebra with no oriented cycles and no parallel arrows and no subquivers of the form star, this no-nilpotent case, then the Maurer-Cartan elements are of this form. So they are given by two cocycles, okay? With all Fi have to be two cocycles, and we describe all the Maurer-Cartan elements for under our hypothesis. So thank you very much.
Thank you for your nice talk. Are there any questions?